Hi everybody. So we didn't get quite enough time to talk about this in class. So what we're going to do is go through in class number 9 and just highlight a few different pieces and parts of this. So hopefully you get a little bit better sense of how to do these problems, as well as a problem that's a little bit like the quiz, which is problem number 3 on this assignment. So for the first one, the idea is that our computer chip is steady state. That means it's not changing temperature. So because it's not changing temperature, right, delta S for a solid is CV times the log of T2 over T1. That's from our note sheet. Because we're not changing temperature, we're not changing entropy. So we can write a rate equation. That's just the rate version of the equation that we wrote in class. We're not changing entropy of the chip itself because it's, again, not changing temperature. We don't have any heat flowing into the system. So Q in is 0. Heat is flowing out of the system. It's flowing out at a rate of 25 watts, which we'll put here on the top, and it's flowing out into the room. The room is the temperature here on the bottom, 293 Kelvin. So we have 0 equals 0 minus Q over T plus gen. So we get that the entropy generated is 0.085 watts per Kelvin, which tells us S gen is a positive number. That means, yes, spontaneously heat will flow from this 60 degrees C computer chip out and into the room at 20 degrees C. That's a spontaneous process, right? Heat flows from 60 to 20. Shouldn't be very surprising. But that's how we can start to use SGen. What we're going to do in problem 2 is look, essentially, this puts together kind of a couple pieces. I'll highlight a couple things from the problem statement. We have water boiled at 100 degrees C in an open, well-insulated vessel using an electric heating coil. So what that means is this is a constant pressure process. It's an open vessel. We're not the water is going to always be at atmospheric pressure. We're putting heat in from an electric coil. We're using a constant 500 watts. So that would be Q dot is 500 watts. That's heat that we're putting in. We're putting it in as electrical energy, but then it's turning into heat because of our resistive heating coil. Then what we're going to do is we're going to run that for 5 minutes. We find that the mass decreases by 0.066 kilograms after 5 minutes. So we boil 0.066 kilograms in 5 minutes. So this is admittedly fake experimental data, but this would be how we can determine both the enthalpy of vaporization, HFG, and the entropy of vaporization, SFG, for the water. So how do we do this? Well, we have a 5-minute experiment, so we want to find the total amount of heat. So Q is 500 watts times 5 minutes times 60 seconds per minute. So this would give us 150 kilojoules of heat. That's how much heat we're putting into the system. If we are, right, Q 1, 2 equals delta U plus W. This is delta U plus the integral of P dV. This just so happens to be a constant pressure process, so we can pluck that little P right outside of the integral. This equals delta U plus P delta V. This just so happens to be delta H in disguise. We did one more problem like this. You're not going to have to know this for an exam or something, but that's what that is. So our equation Q12 is equal to delta H. So we're essentially asking, where is that heat going? It's going into the vaporization of water. So the change in enthalpy that we're seeing is exactly HFG. So this change in enthalpy is 150 kilojoules. Little delta H equals big delta H divided by the mass, which is our total enthalpy is 150 kilojoules. That's how much heat we put into the system. It goes in as enthalpy. And then we put that into the water that was boiled. So the water that didn't boil didn't actually experience an enthalpy change. It's still liquid. It's still 100 degrees C. Only the water that actually boiled experienced a change in enthalpy. So this gives us a change in enthalpy of 22, 72, or 73 kilojoules per kilogram. So that gives us HFG. Now to figure out entropy, the change in entropy of our control mass is equal to Q in over T of our control mass minus Q out over T of the surroundings plus S gen. So if we assume that we're doing this reversibly, then no entropy is being generated in total. This is true if we're heating it reversibly. If we don't let the gas cool down, there's no heat that's actually leaving the system. If we've insulated our pot, we're not letting things cool down. So this is insulated pot of water. Then we can find the change in S of our control mass equals Q in over the temperature of our control mass. So this is equal to 150 kilojoules divided by 373 Kelvin. And then we can add mass into the equation just the same. So we could say that delta S is equal to, so now lowercase s is equal to 2273 kilojoules per kilogram divided by 373 Kelvin. Delta S is equal to SFG because that's where that's what happened in our system, and that equals 6.09 kilojoules per kilogram Kelvin. So hopefully you can see a little bit how we might be able to do experiments to calculate things like HFG, SFG. We can use this equation here about entropy generation in order to be able to do that. If we compare this with the book values from our tables, HFG under these conditions is 2257 kilojoules per kilogram, and SFG would be equal to 6.048 kilojoules per kilogram Kelvin. So this is fake experimental data. I made it up so we weren't exactly right, but we're close-ish. And we can imagine doing more careful experiments to get more accurate information. All right, the last thing I want to quick cover is number 3. And number 3 is a little bit like the quiz that we just had. It's essentially asking us to find all of the things, to find W, to find delta U, and to find Q for a problem, and then to find delta S for the problem. The difference is this is a different process. So if you want, if the quiz was a challenge for you, you may want to pause this and not look at it and just see if you can solve this yourself. There will be a problem sort of like this on the final. In this particular process, we have a compression from 100 kPa and 10 degrees C up to 450 K. Now, what we're always asking ourselves in these cases is what's the process? What's the pathway? This particular system is a polytropic process. So when we're looking at calculating W, when we're looking at calculating Q, we have to know those are path dependent. We need to follow now a polytropic process. So what do we know about a polytropic process? Well, we can look at our equation sheet and find an equation relating pressure and volume. But we don't have pressures and volumes, so we'll look at a little bit maybe up from that in the same location and find one with the variables that we happen to have for our specific problem, temperature and pressure. Our polytropic exponent n of 1.25, we were given that on the problem. That can simply fit right there into the equation. And we can calculate a final temperature T2. So our pathway tells us, again, kind of that second piece of information that we need to be able to figure out what the final state is. Then we're looking at an equation like this one for work. This is a path-dependent equation. We need to figure out what n is. For a polytropic process, this value of n is just 1.25. It's just the value. If we had a different process, like a constant volume process, then n is infinity. And we can use the same equation, but we have to put a very different value of n. If we had a constant pressure process, then n equals 0. If we have a constant entropy process, a delta S equals 0 process, then n equals K, equals this ratio of the heat capacities. So calculate work, we can use the same equation for a lot of different processes, but we have to know which pathway, which process we're actually talking about. That can give us W. Delta U is always easier because that's a path-independent thing. Delta U is just CV delta T, and it doesn't matter what pathway we're going on, we can just use CV delta T. Then we can put these two together, put together what we found for work, and Q, we can put them into an energy balance down here and find our final value for Q. To find entropy, we're asking ourselves really, are we a gas or are we a liquid/solid? If we're a gas, we have two equations that look sort of like this one with the arrow next to it, and we can choose the one that we happen to have the best data for. So for this one, we know temperature and pressure, so we'll choose this temperature-pressure version, and then simply plug in the different values, make sure that temperatures are in Kelvin, and that can give us a final change in entropy. This is a negative value, that's okay. We're allowed to have negative values so long as we had a bigger positive value somewhere else. We're just looking in this case at the change in the entropy of the gas. There's heat transfer going on. We're actually, right, what we can see here highlighted, we're losing 44 kilojoules per kilogram of heat. That heat's going somewhere. It's causing an increase in entropy, Q over T. We don't really know exactly where it's going in this one, but that would be causing an increase in entropy bigger than our decrease in entropy. If we were to put it together with the equation like we did for problem 1 and 2. All right, hopefully this was helpful. Give kind of a sense of how we can fit together some of the different equations that we have used throughout the semester and use those for problem solving. Feel free to reach out to me if you have any questions or if you're still confused or want to work through some examples together. There are some additional examples for entropy generation. You should make sure to watch. They should be helpful for going over the homework for this week. Otherwise, I look forward to helping you wrap up the semester. I hope it goes well for you, and we'll see you back in class.